Now we'll make an alternative formulation for the beam element. Instead of using the classical Hermitian polynomials and the nodal displacement, I will be using a general displacement interpolation like we did in the Rayleigh-Ritz method. Okay, so beam element with general displacement interpolation. So what we are doing here is as follows. So instead of defining shape or trial functions, let's write shape functions in terms of membrane forces. Sorry, membrane degrees of freedoms, membrane degrees of freedom. Let's define them in general polynomial terms. Again, I'll just write everything in natural coordinate system. So we have d1 coefficient plus d2 psi plus d3 psi squared plus d4 psi cubed, and so on. And in that case, where psi is equal to 2x minus L over L, the same variables that we use in the Hermitian polynomial case. Now I will be using Legendre polynomials for the interpolation. I'll just write down what they are and plot them. It has the form as mentioned here. V psi is equal to L1 psi multiplied by D1, first Legendre polynomial, the second one D2, the third one D3, and the fourth one D4. And these polynomials are as follows, where L1 is equal to 1. L2 has a linear variation psi. L3 is equal to 1 over 2 3 psi square minus 1, and L4 is equal to 1 over 2 5 psi cubed minus 3 psi. So let's plot them. So let's draw a coordinate axis. So the first function will have a constant value. So that's L1. It's always equal to 1. The second function varies from -1 to 1. So it will have a... It's difficult to draw. Let's see if I can do it. From here to there, it will pass from 0. That's L1, and that's L2. L2 has a linear variation. Now let me plot L3. L3 will have a variation as follows. That's L3, and let's use a different color for L4, and the variation of L4 will be as follows. So this is L4. So when you examine these curves, here L1 represents rigid body translation. L2 represent rigid body rotation. So we have two rigid body modes in this polynomials. L3 represents, let's put S's here, symmetric bending. And L4 represents anti-symmetric bending mode. So that's my interpolation function. So I need a relationship between these interpolation functions and the nodal displacements, or the displacement field of that member, so that I can write down the energy equations. Now, if this is the displacement interpolation that I have, my rotation interpolation will be the first derivative of it. That will be equal to dv psi d psi. That will be equal to L1 prime psi d1 plus L2 prime psi d2, L3 prime psi d3, and L4 prime psi d4. And I can write the curvature in the following way, right? The curvature psi will be the second derivative of the displacement interpolation, and I will just show it this way. Now let's write everything in matrix form. V is equal to L1, L2, L3, and L4 multiplied by D1, D2, D3, and D4, right? So that's equal to L times D. The curvature is equal to L double prime, the second derivative of the shape function, second derivative of the second shape function, and the fourth derivative, second derivative of the fourth shape function, D1, D2, D3, and D4. So that's equal to L double prime D. So that's my kind of B matrix, because these here doesn't represent the displacements, right? They are not nodal displacements, but that's a general interpolation. Now let's write down the internal strain energy. Or let's start from the total potential energy functional. So I'm just following the same path that we did for the other two truss and beam elements. So P is equal to U minus W, but here I'll just focus on the U is equal to bending deformation only. We have from 0 to L, 1 over 2 curvature. Let's write it this way first. 1 over 2 K times EI times, sorry, just keep writing the same thing over and over. 1 over 2 V double dot EI V double dot dx. And that's equal to, that's the curvature. So we have the curvature interpolation here. The transpose multiplied by L multiplied by EI times L multiplied by D integrated over the length of the member. And let's call this one equation 1. And when we evaluated that part of the equation, we know that that's our stiffness matrix. But let's call it KK, and that's our stiffness matrix. Defined in the general displacement field. So this stiffness matrix by itself doesn't mean much, because the variables that it uses, D1, D2, D3 and D4, is not something that we physically identify. So what I want to do is to convert these displacements into the nodal displacement that we usually use, okay? So I will try to relate the nodal displacements with the general displacement coefficients. So remember that that's our beam, that's node I, that's the jth node, okay? So we can say that at x is equal to 0, Vi is equal to 0. And also theta I is equal to 0. At x is equal to L, Vj is equal to 0, theta j is equal to 0. So these are the boundary conditions for this beam element. Now if I use psi at x is equal to 0, put x as 0 into that equation, we get -1. So here it means that the psi is equal to -1. And at x is equal to lab, put L into that equation again, you'll find out that psi will be equal to 1. So what I need to do is to find out a relationship between the nodal displacements Vi, theta I, Vj, theta j. Between D1, D2, D3 and D4. I have to correct something. These are not equal to 0. Sorry for this confusion. Let me correct that. V will be equal to Vi. The rotation must be equal to theta I. Okay. The translation must be equal to Vj. And the rotation must be equal to theta j. So the first relationship, what is the relationship between Vi and D1, D2, D3 and D4? So I have the displacement interpolation here. That's my displacement interpolation. So instead of psi, I will put -1 into it. So V minus 1 will be equal to L1 minus 1 D1 plus L2 minus 1 D2, L3 minus 1 D3 plus L4 minus 1 D4, right? And we said that the displacement at psi equal to -1 should be equal to Vi. And when you evaluate that, you obtain Vi as equal to D1 minus D2 plus D3 and minus D4. So my first row of this matrix is equal to 1, minus 1, 1, and minus 1. Okay, so and then you repeat the same procedure. For the rotations, we have the following equation. Instead of psi, we put -1 and obtain whatever we get in that equation and write it here. And for the second row, this is 0, this is 2 over L, this is -6 over L, 12 over L. The third equation that relates Vj and these D parameters are 1, 1, 1, and 1. And the final equation is 0, 2 over L, 6 over L, and 12 over L. So I call this matrix as my nodal displacements, U. That's the G matrix. It's a transformation matrix between the nodal displacements and the general displacement variables. And let's call this one as our general displacement coefficients. So in that, let's write everything in matrix form. U is equal to G times displacement. So if I know what D1, D2, D3 and D4 is, I can directly calculate the nodal displacement by using this transformation, this G matrix. And I can do the reverse. D psi, D will be then equal to the inverse of G multiplied by U, right? So let's call this one as our new transformation matrix. That will be H. So this transforms the nodal displacements into the general displacement coefficients. So in that case, I can write the following. D instead of D, I have H multiplied by U. So let's call this one equation star, and remember that I have written this stiffness matrix equation in terms of D. Now if I put this equation into equation 1, I will obtain the element stiffness equation for the nodal displacements. So let's do that. Inserting equation star into equation 1, we have the following relationship: UE is equal to 1 over 2 from 0 to L, U multiplied by H transpose. I have the second derivative of L transpose multiplied by EI, L times H times U integrated over the length of the member. And we already say that this is equal to, or I can just write it in this form so that it's easier. I have the U transpose, H transpose. I have the element stiffness matrix evaluated in the general displacement field multiplied by H U dx. And this equation is the classical element stiffness matrix that we know. So this H matrix relates general displacement with nodal displacements, and this transformation transforms stiffness matrix in general displacements to the one in nodal displacements. Okay, let's go back and go over very briefly what we did. Now in the previous formulation we used the nodal displacements as our displacement field in the interpolation of the displacement field. But here I'm just showing that I don't have to do that. I can actually define any interpolation function. Of course, I have to make sure that it is admissible function. So here I use the Legendre polynomials. So I have some displacement terms, d1, d2, d3, and d4, but they have a different meaning. For example, we can say that d1 tells us how much rigid body translation in this element. Likewise, d2 can tell us how much rigid body translation we have in this element. So it's a different displacement definitions. So with these definitions, I have the displacement interpolation here, and that would be the rotation interpolation. And when you take the second derivatives of this function, you'll get your curvature definition. And the rest is very actually straightforward. You write down the total potential energy functional, and all you need is the curvatures. You have it here, and you get a stiffness matrix. But this stiffness matrix is written in terms of the general displacement parameters. So we cannot use such a stiffness definition in our classical solution. So I have to transform that into the nodal displacements again. So in order to do that, I have to relate the general displacement quantities with the nodal displacements. So at psi equal to -1, V should be equal to Vi, theta should be equal to theta I. And likewise, at psi equal to 1, I have to have following relationship. So by just relating the general displacement field with these requirements, I obtain a transformation matrix. Okay, this transformation matrix helps me to determine the nodal displacement from the general displacement quantities. So that's my equation, but I can just reverse that equation. If I take the inverse of this G matrix, I can directly relate the nodal displacements with the general displacements. So if I plug that relationship into the stiffness matrix equation, I find out that I have to transform the displacement stiffness matrix defined for the general displacements with the following equation, and this one will convert it into the stiffness matrix that we know. So now let's take a look at the implementation of the beam with the general displacement interpolation. Remember that in this case we were using the following equation for the displacement interpolation. The transverse displacement is equal to, we have L1 psi multiplied by D1, L2 psi D2, L3 psi D3, and L4 psi D4. And these functions L1, L2, L3, and L4 are the Legendre polynomials. And these D1 coefficients, they are some coefficients, but they are not related to the nodal displacements. Now let's take a look at these Legendre polynomials. We have L1 is a constant, it's this red one, which represents the rigid body translation of the member. Now L2 is psi, it's that blue line that represents the rigid body rotation of this member. So when we say rigid body, actually we are meaning that the beam moves, but we don't see any deformations, any strain in the beam. We will see some translations at the node, some rotations, but these translations and rotations do not cause any strains, any deformations in the beam member. Now L3, this one, it is that green line which represent a symmetric deformation under symmetrical bending, and L4 is that pink one which represents the deformation under anti-symmetric bending. So we have these different forms of deformations, and these are the coefficients that tells us how much deformations, how much displacement we get from each deformation mode. Now, and you see this is the first derivatives, and these are the second derivatives of the deformation modes. And when you look at the second derivative of L1 and L2, you see they're all equal to 0. So which means that the rigid body translation and the rotation do not cause any curvature in this member. With the symmetric bending, we have a constant curvature, anti-symmetric bending mode, a linear curvature. So what I did here is I take the second derivatives and plot them. All right, now our next task is to have a natural coordinate to Cartesian coordinate mapping. So these equations are written in the natural coordinate system. So I just drive the equations for the Cartesian coordinate system so that I will get equations for the mapping between the D1s and the nodal displacement. So what I did here, this is our typical equation. These are the Q. I call them Q in this implementation, not D. So instead of psi, I put 2x over L and evaluate them symbolically. This is what I get. This is the equation represented in the Cartesian coordinate system. So I just rewrite that equation here. I copied it and put it in here. And then I take the first derivative of that equation. Remember that the first derivative of the translation, vertical transverse displacements, give me the rotation. And this is the equation for the rotation. Now remember that I need a relationship between the nodal displacements and the coefficients that I used in the transverse displacement interpolation. And our relationship is as follows. So at x is equal to 0, v should be equal to vi, theta should be equal to theta I, and at x is equal to L, v should be equal to vj, and theta should be equal to theta j. So I get the relationship between this interpolation function coefficients and the nodal displacement. So for that, I just put 0 here, and that's the output of that equation. I put L here, that's the output of the equation, and that's Vj. For theta I use the following equation. I put 0, that's the relationship between theta I and the polynomials. We can just say this, the Vi is equal to Vj is equal to theta I is equal to, and theta j is equal to. And then remember that we have written the following. So U is equal to G times, let me use this X here, Q, or in matrix form, I can just write this one, Vi, theta I, Vj, and theta j is equal to this transformation matrix multiplied by Q1, Q2, Q3, and Q4. And when you take a look at this matrix, this is nothing but rewriting this equation in matrix form. So Vi is equal to 1 times Q1 minus 1 times Q2 plus 1 Q3 minus 1 Q4. Right? So we said that, okay, that's the relationship between the nodal displacement. So if you know the polynomial coefficients, you can obtain the nodal displacements. So in order to get the reverse relationship, I multiplied both sides by the inverse of G. So I can just write Q is equal to G inverse multiplied by U, and we call this one as our H matrix. So here I'm taking the inverse of G, and this is the output. So I evaluate that symbolically and I get my H matrix here. Now next step is to calculate the stiffness matrix. So first we will calculate them in the general coordinate system, and then I will transform that into the Cartesian coordinate system, or the system that has the nodal displacements. So let's take a look at the interpolation. So this is our L functions. So I'm taking the second derivative. So as expected, the rigid body translation and the rigid body rotation do not cause any curvature. And these are the constant curvature and the linear variation in the curvature. These are the equations for that. And in the variational formulation, we obtain the equations. So our KK matrix, the stiffness matrix in the general displacement field, is evaluated like that. So I didn't use the natural coordinate system, I evaluate it in the Cartesian coordinate system. So this is from 0 to L. I have the x here, EI. This is the B matrix, B times B transpose. So in the notes we have the reverse. I have written it in the reverse order. But here I just want, for visual purposes, I define the curvature interpolation as a vector. So I just reverse the multiplication here. So when you evaluate that expression symbolically, this is what we get. So what this matrix is telling us is as follows. Remember that our first mode of deformation is the rigid body translation. There's no resistance to it in this member. The second one is the rigid body rotation, no resistance. That represents the resistance of this member to symmetrical bending. Okay, it's 144 EI over L cube. And the fourth deformation mode is the anti-symmetric bending, and that's the stiffness, that's the resistance we get from the member. And as expected, the resistance to anti-symmetrical bending is almost 10 times larger than the symmetrical bending. And as you see, we don't have any coupling between the different deformations modes. Okay, but of course, that's a very nice stiffness matrix, very simple one, but we cannot use it in our typical finite element solution. So I have to convert them into the nodal displacements. So in order to do that, we will just use the transformation that we derive again in the variational formulation. The transformation matrix transpose multiplied by the stiffness matrix times the transformation matrix itself. And at the end of the day, again, we get our final stiffness matrix. And this is also the same matrix that we obtain with the Hermitian polynomials, the same matrix that we obtain with the stiffness matrix derivation. So if I get the same matrix, I can basically say that the beam element that we derived has actually 4 deformation modes. Okay, one of them is the rigid body translation, rigid body rotation, symmetrical bending, and the anti-symmetrical bending. So basically we can just conclude that the combination of these 4 bending modes will give us the full displacement field of a beam element derived by the stiffness method.